This is part 7 in a series of videos in which I'm attempting to repair this Wren executive computer. In the previous videos I've got as far as replacing a few faulty ICs, mostly memory chips, and I've been showing how I go about the basic fault finding. Before we look at the Wren, I thought it would be worthwhile just explaining the purpose of my channel. From the previous few videos I've had some very interesting and useful comments. Ideas like, oh, I could just shotgun the board and replace all the logic ICs, giving more information on the various ICs, this sort of thing. I'm aware that some of these video series do tend to get a bit long, so I do try to minimize them whenever I can, and that does mean skipping over quite a few of the steps involved in the fault finding process. However, if you're interested in seeing those steps, then please let me know. It's just really trying to strike a balance between what you find interesting and not making the videos too tedious. Anyone that repairs these knows that quite often there's a lot of steps that you just kind of do automatically and don't really consider them to be worthwhile showing, but if it's the sort of thing you want to see, then please let me know. I've been repairing this sort of thing now for around 50 years, and the main purpose of my channel is to try to gain exposure and make people aware of these machines, as well as hopefully providing some interesting repair videos. Most of the items I repair I don't own. This is not my machine. It belongs to somebody else and I'm repairing it for them. I don't normally charge when I repair machines. The only thing I charge for are the replacement parts, which is why I try to minimize the number of parts I replace. Sometimes I might take parts out, but if they work I'll socket them and put them back. As I said, I don't charge for my time, I only charge for the parts I replace. And the real reason I'm doing this is to try to, as I say, promote these old machines. They are very interesting, both from a technical point of view, but also from a historical point of view. My channel's not monetized. I don't make any money at all doing this. This is just done purely for hopefully entertainment and making people aware of these machines. Also, I would like to try and get across the various repair techniques that I've developed over the years. There's many different approaches I take, and I'm trying to give a good spread of those on the videos. It's not necessarily the most efficient or effective way to repair a particular machine, but once you've seen the different methods that you can use, then hopefully you can pick the best approach that suits what you're repairing and the equipment that you have. It will vary from person to person and whatever preferences you have, and also of course the faults that you find. There are an almost infinite number of ways you could approach repairing something like the Wren, for example. This is one of those machines that was designed in the early 80s. That's a real kind of ad hoc approach to design, where the glue logic is just a compounded rat's nest of logic, and without the schematic, which I don't have, it's very difficult trying to navigate your way around. It's not designed as you would a modern computer system. It's a very kind of messy design from the glue logic perspective. Also, I was asked to give more information on the major chips, which I will do that once I get them online. I'll show you a bit more of what I've been working on in a few minutes. But one of the first things I do when I start working on a machine is, in general, I've done so many machines of this era that I tend to have all the data sheets printed off, but sometimes I'll create a specific worksheet where I'm identifying certain lines that don't seem to be doing what they should. I then get a spec sheet for all the major components. Most of the glue logic, like everyone else, I now am familiar with, so I tend not to need the data sheet. But all the bigger chips, the large-scale integration chips, I tend to get at least the pinout for them, so I can do some sensible testing. But again, if you want me to go into more detail as to how these devices work, then please leave a comment, and as I get each one working I will go into some more detail, not just about the particular chip that's fitted, but also possible alternatives. So for example, with the CRT chip that's fitted to this, there are alternate types that you could use in place of the one that's in here, and quite often machines like this are not repaired or even scrapped because there's a belief that certain devices are not available anymore and they're obsolete or cost hundreds of pounds, hundreds of dollars to find replacements. And quite often you'll find that there are very readily available low-cost alternatives. So for example, with the Z80, we've got a Z80 in this machine, but if you take a look at the device that's actually in here at the moment, the Z80 in this had failed, but this device is a D780C, and it's kind of the industrial version of a Z80. In general, they tend to be the high performance version of the Z80, so I tend to use them for most testing that I do. So I'll pop even if it's working, I'll pop the original Z80 out and put one of these in, and they tend to have good drive characteristics. So I'll put one of these in, do the testing, and once I've got the initial faults resolved, I'll put the original Z80 back in, or a more standard Z80, and then retest it. Also steps such as generating documents like this. I showed this in the previous video. This is the Intel hex file for the ROM in this machine. If you want to see how I go about doing this, then let me know. I also showed a decompiled listing, so if you want to see how I go about doing that, again, drop a comment. Also, in the previous repairs I've done, I've mentioned and shown some software utilities that I've written, and quite often in some of the bigger repairs I'll write possibly numerous software utilities to do certain data conversions. I don't normally spend more than an hour or so writing each one, so I tend to treat them as throwaway steps, but again, if you want to see how I go about doing that, then let me know. Okay, so as I said, that's the basis of my channel, is just to try and promote this old equipment, show some interesting or hopefully interesting repair videos and techniques that I use for going about repairs. In the upcoming videos you see lots of different methods that I use, and which particular one I employ would normally come down just purely to the machine I'm working on and the fault I'm trying to track. But in the videos I'm showing here, I'm tending to take a bit of a more long-winded approach, just to give you some ideas as to the various different methods that you could use on this particular repair. So onto the Wren. I got as far as it actually running to the point where it was doing the self-test. Now, self-tests are quite useful to a certain degree. The problem with most self-test systems is they tend to need the system to be working to start with, otherwise the self-test itself gives fairly erroneous results. And when I first started working on this, it wouldn't run at all. The Z80 was completely dead, and it turned out that there were failed memory chips, and then I found that it was very flaky in its boot up, and it wouldn't complete the first part of the self-test. And I showed that in the previous video, where using the logic analyzer we could see that it was just going round and round in a small loop in the firmware. I didn't scroll beyond certain points in that because it wasn't ever leaving that loop. So once I'd figured out what was going on, that was just a failing buffer chip. It did start getting to the point where it was going into the self-test. In other words, it was actually running some code. But in order to do that, it needs to carry out certain fundamental tests. So if I just prompt a failure or force a failure, I'll remove one of the memory chips. Okay, so I've taken out one of the DRAM chips as a set of 8, and what should happen now is there's a self-test the machine goes into when you boot it up, and the first one is it's a bit walking self-test within the DRAM. So if I power the Wren up, then what we'll see is the power light should come on continuously. If I reset the machine, if we watch the caps lock light and the power light, so that's a reset, you'll see the caps lock light comes on, and it stays on while the self-test is being carried out. It went off fairly quickly. I'll do it again. Hopefully you can see this on camera. Okay, so it comes on very briefly and then the self-test terminates, and it's terminated because the self-test has failed. The failure or the error is indicated by the number of times this power light flashes, and you can see here it's flashing once. And the error specified in the manual for one flash is walking bit test on common RAM, and it specifies it as being in memory address F0000 to FFFF, which is quite useful information in itself. It tells us where the RAM is mapped to. Although if you recall, the fluke can't see any RAM, so there's something else going on somewhere. Okay, so I'll power off the Wren and I'll put the IC back in. And if we now power the Wren back up, so I'll do that again, I'll press reset. You'll see the caps lock light now comes on for much longer. It's running the self-test, and then we see the power light flashing again. If it completes the self-test, the power light will stay on continuously, and the display should in theory show the welcome screen. Now there's several things to note here. Firstly, the fact that the caps lock light and the power light are being controlled means that if nothing else, we know the processor is running and the system is working to a certain extent. We also know that the RAM must be operational to a certain extent as well, because there's a timer that's used to time this light. Now it could be a hardware timer, of course, but looking at the firmware and what I've seen so far, I believe that's a firmware loop where it uses a value in the SRAM to time this caps lock and also to time the flashing of the power light. So we're getting 6 flashes. That means that the error is a loopback test failure for the UART. There is a loopback test within the UART chip itself. That's this large scale device here, and the loopback tests are quite often fairly pointless in these devices. There's a bit you can set in the control registers within the device, and what it does is it causes the output shift register to be shifted or transferred directly into the input shift register. So it allows you to kind of send data and read the data back at the same time. But it's fairly pointless, to be honest, because if you can put it into the loopback mode, it means you can read and write to the control register within the device anyway, and you use the same data bus and address and control lines to do that you use to read and write the input and output registers. So in other words, if you can put it into the loopback mode, the loopback mode test is fairly pointless because you've already proved that the device is working to that extent. Generally speaking, loopback tests are only really useful when it's a loopback of the output from the machine looping back into the input, and that's generally done on more advanced machines using some device to switch the output to the input and to disconnect the output from the socket just in case something's plugged in. In this case, however, it's a fairly moot point because the device is never actually been addressed. If we look at the spec sheet for this, we'll see that the CEN line, which is the chip enable line, is never been asserted. It's active low. It doesn't say on here it's active low. And if we look at that on the scope, you can see that line is permanently high. Now, of course, this is all derived from the in-out system, the in-out decoding, and that's what's not working on this machine at the moment. The in-out decoding for the peripheral devices isn't working. Now, we can test other parts of the system by forcing some failures. So if I pop the ROMs out, then it doesn't boot up at all, as you'd expect, and that does again tend to prove that the ROMs are accessible. We know that anyway because the system is performing some fundamental self-tests. But we can do other types of testing. So for example, if I pop the real-time clock chip out, Incidentally, when I'm using a screwdriver here, I'm not levering it up and possibly damaging the board. What I'm doing is I'm kind of wiggling it side to side and trying to use the width of the blade of the screwdriver to kind of pop the leads vertically upwards. Don't be tempted to lever it like this, because you can very easily damage the board. Okay, so I've removed the real-time clock chip. I've powered the Wren back up. So you see it's still flashing 6 times. The failure for testing this device is 9 flashes. In other words, what it does, it gets as far as testing a particular part of the system, and if that fails, it just keeps looping around indefinitely trying to retest that part of the system. So we can't test the rest of it until we get the test to pass that's currently failing. And looking at the list of tests and errors, it looks like this is really the first test, and it's doing this loopback test, where it's trying to address a peripheral device. The only thing here is that while there's a keyboard controller device, which is this device, we are getting lights flashing on the keyboard. The next thing I'm going to do is see what's actually driving those, because it might just be its discrete logic that's doing that, rather than it being the actual keyboard controller. In which case it would again confirm that none of the peripherals are being accessed at all. And unfortunately this is a real rat's nest. I do have other information on the documents I have, and for example video is shown at 4000 hex to CFFF, and that wasn't detected by the fluke either. And there is some additional character RAM as well, and that's at 7600 hex to 85FF hex, and that wasn't detected either. I find it unlikely that those areas are banked out, or at least not available in every bank, because it would make the system very inefficient, but it is perfectly possible that they just weren't in the bank that the fluke has access to. But it does seem odd that none of that is available to the Z80 in all banks. So really the next step is to start looking into the in-out decoding. Here is where a schematic would be extremely useful. It would just take a matter of a few minutes to trace through and see where it's failing. But because of the way that the in-out line goes all over this board, and the various parts, so for example you'll get an in-out that's being combined with the M1 line from the processor to control when certain in-out functions occur, and then the output of that signal again fans out and goes all over the place. So it's very difficult trying to figure out exactly how this in-out system is structured. Okay, we can do a bit more testing on some of the actual memory devices. If I pop out one of the video RAM chips and now power up the Wren, so you can see it did a fairly brief self-test. Only got so far through the self-test, and now we're getting 2 flashes on the power LED, and that's specified as being the character RAM failure for the video. And of course it's because we've taken the RAM out. So again, we know that the video RAM is working to a certain degree, because when I had the RAM chip in, it was passing this particular test. But the various things that are specified for this machine are what are causing the confusion here. The banknote RAM is specified as being at 0000 to EFFF, and the fluke couldn't find it. So it does tend to indicate that the way this machine is laid out, there is some interaction between the in-out decoding and the RAM access. And it's not necessarily that surprising, but it does make fault finding without a schematic very difficult. So the next thing I'm going to be doing is looking through the in-out system, trying to trace exactly where it goes, and see if I can figure out why none of the peripheral devices are being addressed, even though the machine can obviously access its entire RAM space. to assist in doing that, what I've started with is the decompiled version of the code in the ROM. And if you read through this, you'll see that dotted through it there are various out instructions. Now you do need to be a little cautious when looking at a decompiled version of code, because decompilers often can't tell the difference between data and blocks of data within the ROM. So it might be a text string, for example, and actual code, and sometimes they will find what is just a simple data text string or block of data and start decoding it as instructions, and that can throw off all the remaining instructions for the rest of the file. So you need to be fairly careful. However, what I've done is gone through this. Again, I wrote a very small utility that just searched out all in and out instructions and then recorded the unique addresses. And so what I ended up with is a table like this. Now normally I wouldn't print all this out, I'd just do this in my head and then just go through the board and test all this, but for the purpose of the video I thought I'd just show this. So what we have here is the in-out map or in-out port usage for the Wren. So port 0, and again the way that the in-out system works on the Z80, it's completely separate from the memory space, and in addition you can split out RAM from ROM fairly easily with the Z80, which I suspect is what's going on here and why the fluke can't find the RAM. But the way it works is if you look at a port number, then when you issue an in or an out instruction on the Z80, then it will use the lower 8 bits of the address bus as a port number. In other words, that will be this number here, and then that is obviously used completely separately from RAM or ROM access, and gives you a really nice automatic decoding, or these first step decoding for the in-out system. And that's what I believe we have an issue with. So what I need to do is figure out where all this goes and what in particular is not working. And now I have this, there aren't that many. What I have are the addresses for each individual in-out device. Also, you can generally tell by whether they're out and in, or just out or just in, what the device is likely to be. Certain devices you wouldn't read and write, other devices you need to be able to read and write. And of course I can now turn the port number into a bit pattern and see which address bits that match this go to different parts of the system. So for example a multiplexer or something like that. Now unfortunately a lot of the decoding for in-out is done in discrete glue logic, so it's very difficult to follow through. But if I start at the device end, in-out device end, and work backwards from its enable pin, then I should be able to tie it up with one of these at some point, and then I can just add another column that says what each of these ports is actually controlling. And at the end of that I should in theory have a good map for the in-out that will allow me to do some proper fault finding and more easily locate the problem. I could just go through with a scope or with the logic analyzer, but I like to do this by way of demonstration, showing that you can take a fairly methodical approach to this. It certainly beats just randomly probing around or just swapping out parts. I really, with old equipment, try to avoid creating triggers brush. If you don't know what I mean by that, then if you've ever watched Only Fools and Horses, then there was a guy in there that had been a road sweep for 40 years, and he claimed to still be using the same brush that he had when he first started, except that it had 30 new heads and 20 new handles. And I try to avoid that with this. I don't want to replace components that don't need replacing. I want to keep it as original as I can. Sometimes you have to replace parts, of course. If I don't need to, I generally speaking won't do that. That is one of the reasons I built the logic comparator, because it allows me to test for marginal devices, I can just clip it on to a component, and I will get an indication. Because of the way I've got this set up, I will get an indication as to whether or not that component is marginal or working beyond a certain spec. And it's far more useful than just knowing if it's switching yes or no, which isn't always very indicative of a working component. And of course it's far quicker than going round the board with a scope looking for poor signals, which is what I did before I had the comparator. Okay, so hopefully that wasn't too much detail. As I said, if you want me to go into more detail or less detail, then let me know. In the meantime, if anyone has any information, schematics, etc. for this machine, then please let me know. Or any ideas or fault finding tips, then again, please let me know.